So how do we measure these energy changes? How do we know how much energy we get from something? Well, we do have to understand the flow of energy. So energy is always flowing to or from a system or in and out of the surroundings. And so our system is basically whatever part of the universe, the change that we're going to observe. Like if you look on my channel, I did a demo video for one of my other classes where I did a bunch of reactions inside test tubes. And so in those reactions, my system was whatever was happening in the test tubes, and then the surroundings is technically the rest of the universe. But when we think about a reaction, we're just looking at just the individual area around that. So like I did these reactions in my garage. So my garage was my surroundings. The rest of my house, not so much. Here in my office, I have to go into the laundry room, through the kitchen, through the living room, down a hallway. And so in my office, I'm removed from my garage, plus my office is more insulated than my garage is. And so this would be the rest of the universe. So system would be my test tubes, my surroundings would be my garage. All right, and so we can look at this. And so we've got a negative change in energy if energy leaves the system because the system's giving off energy, and then a positive energy change if the energy enters the system because it's absorbing energy. This can be a little bit counterintuitive because if a system's giving off energy, we perceive that heat. And so what we are perceiving, we are the surroundings. So we are getting the heat. So the system is giving off the heat. So for the system, it's a negative change. For us, it's a positive change. So for the system, it's a negative change. But for us in the surroundings, it's a positive change. So like when I hold a coffee cup or my tea right here, which has actually gone cold, but when it was first made, it was nice and hot. It was giving off energy. So my system had a negative change in energy. Well, I had a positive change in energy. Okay, and so when we look at this, our change in energy is just the final energy minus the initial energy. If we're looking at a chemical reaction, it's the energy of the products, because that's the final state, minus the energy of the reactants, because that's the initial state. Okay. And so we can look at these sign conventions for the change in energy. And basically what it comes down to is if both our heat and our work are positive, our change in energy is positive. If both heat and work are negative, the change in energy is going to be negative. But if we have opposite signs for those, you have to do some math and you have to look at the size of Q and W and see, if one overrides the other, what we end up getting for our change in energy. So we can look at something like this. So I've got this picture down here where I've got my system and my surroundings, and I want to know A, B, or C, which one's going to represent when the system is losing energy. So the system's going to give off and the surroundings are going to gain. So my initial conditions, I have 3/4 tick marks for my system, and my surroundings I have 1/4 tick mark. And so is there a picture A, B, or C where they change by an equal amount? One goes down, the system goes down because we want a negative delta E, and the surroundings go up. Well, if you look at the pictures, both A and B show a loss of energy from the system. C shows a gain of energy in the system. So C is not correct. So we'll cross out C. C is not correct because the system gains energy there. So it's either A or B. Now in A, the system goes down by 1 tick mark and the surroundings go up by 1 tick mark. In B, the system goes down by 1 tick mark, but the surroundings do nothing. Now, when energy moves around, what happens to one, the opposite has to happen to the other. So if my system gives off a certain amount of energy, my surroundings have to gain an equal amount of energy, which means that we're going to go with A, because the system goes down by 1 tick mark and the surroundings go up by 1 tick mark. Okay, and so we get various different units for energy. So joule, calorie, kilocalorie, capital C calorie. If you look at these, you will see that the capital C calorie and the kilocalorie are exactly the same thing. And so when you look at your food labels, you see it's a capital C calorie. Right? So this gives us our first law of thermodynamics. I'm going to have to put the equal sign over here. There we go. Okay, so what our first law of thermodynamics says is that the total energy of the universe is constant. So energy can be neither created nor destroyed. So what goes in must be what comes out. We also call this the law of conservation of energy. So I can transfer energy between the system and the surroundings. I can convert energy from one form into the other. So like if you've ever had your cell phone, so your cell phone is using electrical energy, all right? Now, if you've ever used your cell phone and it started getting really hot and you noticed the battery started draining faster, what was happening there is that the electrical energy that your phone was producing, a lot of it got transferred into heat energy. And so your phone starts to overheat, and so your battery goes down faster. So you didn't lose any energy, it just got converted into heat energy. And so the change in energy of my surroundings plus the change in energy of my system must equal 0, which is why our previous example, we had to go down by 1 tick mark while the surroundings went up by 1 tick mark. So that's our law of conservation of energy and gives us that first law of thermodynamics. Okay, now when we look at energy flow, we have what we call exothermic and endothermic reactions. And so if I'm giving off heat, it is exothermic. And if I'm gaining heat, it is endothermic. Okay, and so if my initial state is at a higher energy than my final state, I gave off energy, exothermic. If my initial state is at a lower energy state than my final energy state, then I gained energy and it was exothermic. And so you can think of this in terms of water. And so like if you have hot water like I had for my tea, my hot water is giving off energy to the surroundings until it cools down. And so it's exothermic. And again, I'm perceiving that heat change. Endothermic, something like ice. If you leave ice sitting out, ice will eventually melt because ice is gaining energy from the surroundings and it's warming up. And so we end up with our liquid water. Okay. When I look at octane, which is a component in gasoline, okay, it undergoes a combustion reaction. I get carbon dioxide and I get water. And so if I just burn it in like a trash can, I'm just going to get a whole bunch of energy that goes out as heat. Now, inside my car engine, I have my engine, and so I've got these pistons, and so that heat is also giving me some work because as it burns, I end up with some gases forming that create a pressure, which do work, and so my car can drive. When we have food, we do something called calorimetry. And so if we well, we can do this with metals too. So this is just a simple coffee cup calorimeter. And so like I put a sample in there and if it's hot and I have its initial temperature and then I have my water and I have its initial temperature, then the water will heat up and the metal will cool down. And so I can get the final temperature and I can calculate the amount of energy that was involved there. If I'm dealing with food, I can't really heat up a piece of, I don't know, celery and drop it in water. What I end up doing is I have to combust it. And so this is what's called a bomb calorimeter. And in a bomb calorimeter, what we end up doing is we have a situation where we combust a sample, and then same sort of situation, we can lose energy from our sample, our calorimeter and our water surroundings will gain energy, and so then we can calculate the amount of energy from whatever we combusted, like food or gasoline, etc., and we can figure out how much energy is involved. So this is how we actually figure out the energy involved in food. Different fuels are going to have different chemical compositions, and so different combustions of different fuels are going to result in different amounts of energy. And so highest heats of a combustion are going to be hydrocarbons. As we decrease the ratio of hydrogen to carbon, the heat of combustion decreases. And so methane, which is our simplest hydrocarbon, has the highest heat there. And then also if it's an oxygenated fuel, we also decrease the heat of combustion as well. So different fuels are going to give us different amounts of energy.